This is lesson 10 in unit 10. We're talking about representing functions as power series. We saw in our previous lesson how functions defined by a power series behave like polynomials. They're continuous on the interval of convergence, and we found that we could take derivatives and antiderivatives term by term of the given power series. Remember that a geometric series that's in the form a times r to the n will converge if that r value is less than 1. And if we had the common ratio of x instead of r, then we could write that geometric series as ax to the n, and it would be similar to our power series if we compare and contrast the ways that they're similar and the ways that they're different. You can see how the first term is a sub 0, and this goes away. So this is the a value, and in each case here, we're just multiplying by an x, keeping that a value the same, where this one, the a value is changing with each successive step up. So there's a lot of commonalities in power series and geometric series. If we find a power series for f of x is 6 divided by x plus 2, and we're centered at 0, we want to give the first 4 non-zero terms and the general form, and this time we're actually going to find the interval of convergence. So we're going to need to consider the validity of those endpoints. So in our power series 6 divided by x plus 2, we can rewrite that to be 3 in the numerator and 1 plus x over 2 by simply dividing each term out to reduce that down. So we're going to allow our first term to be 3, and our ratio is going to be, we're going to rewrite this to be negative minus a negative x over 2, and that way it'll resemble that summation of a divided by 1 minus r. And we saw if we let a be 1, we could rewrite that to resemble this series from previous sections in our units, where a is 1 and r is x. So considering our geometric series, that's the summation of ar to the n power. We see a and a times r to the 1 plus a times r to the 2, and so forth. Recalling how that's related to the 1 over 1 minus x approach, we have 1 plus x squared plus x cubed, and so on. So let's consider if a is 3 in our sample here, and r is negative x over 2, when we use this formula here, the g of x formula, we can see how in the functions 6 divided by x plus 2, our first term is the a value, which is 3, and then a times the ratio to the first power would be negative 3 times that ratio. Then ar to the second would be negative 3 times the r to the squared term, and then to the cubed term, and that series would look like simplified 3 minus 3 over 2, that should be plus x, plus 3 over 4 x squared minus 3 over 8 x cubed, and then our general term would be 3 with negative x over 2 to the n power. And to find the interval of convergence, we would know that the absolute value of negative x over 2 would converge if that sum was less than 1, because those terms have to get smaller and smaller, and it would converge if the absolute value of x was less than 1. So we can now imply that the interval of convergence would become, let's see, negative x over 2 less than 1 and negative 1. So that interval of convergence would be between negative 2 and 2 because our endpoints are not defined when x is negative 2 here. That would be a vertical asymptote. So we're going to imply the interval of convergence is between negative 2 and positive 2. Another interesting fact is you can find a power series for a rational function by using long division. So if we use example 1 and compare that, dividing x plus 2 into the numerator, 2 divides 6 3 times, and 3x plus 6, subtracting that total, that product, would give us negative 3x. And x divides negative 3x, negative 3 over 2 times, and negative 3 over 2 x would give us negative 3x minus 3 over 2x squared. And then subtracting that total would give us 3 over 2x squared. And we want this to go away, so we need a positive 3 over 4x squared to make this become 3 over 2x squared, and then 3/4 x squared times x would give us 3/4 x cubed, and then subtracting that, we're going to get negative 3/4 x cubed, and then that term would need a negative 3 over 8x cubed. So this would become, so on and so forth, a repeating pattern. And if you look back on example 1, we have the same thing, the same progression. 3 minus 3/2 x plus 3/4 x squared minus 3/8 x cubed to our sum. So they are the same and produce that same general term with 3 times negative x over 2 to the n power being the same as 6 divided by x plus 2, which gave us that pattern, 3 minus 3/2 x plus 3/4 x squared minus 3/8 x cubed plus the general term negative x over 2 to the n, which was a representation of our function, a power series representation. Here's some of the summary of what we've seen so far. We can manipulate series to find other series by using substitutions, by multiplying or dividing the series by a constant or a variable, by adding or subtracting two series together, and by differentiating or integrating a series. So those are the techniques that we've seen to this point. Here we want to find a geometric power series for 4 divided by 2x minus 1. We're centered at 2, and we want to also find the interval of convergence. So once again, I'm reminding you that the series 1 divided by 1 minus x can be written as sigma notation from n equals 0 to infinity, x to the n power, and that it's going to converge if the absolute value is less than 1. So we want to take our function f of x and rewrite 4 divided by 2x minus 1 so that we're centered at our c value of 2. So we have 4 divided by 2, and then our x minus c is going to look like that. and we want to add 2, so we'd need to add 3 to make our term 2x minus 1, because we have 2x minus 4 plus 3 would give us our denominator 2x minus 1. Then rewriting that so that it's in the right format, we want 3 plus 2 times the quantity x minus 2. And I want to factor out 4/3. So by factoring out 4/3, we're going to get it in that form where we have an a value and then 1 minus r. So I'm looking for this form, trying to recreate that form. This would give us our numerator is 1, and then the denominator is going to be 1 plus 2/3, and then the quantity x minus 2. And then rewriting that so we have the proper form, 4/3, and 1 divided by 1 minus negative 2/3 times the quantity x minus 2. That gives me this format that we were looking for, an a number in the top, and then we are going to have the absolute value of negative 2/3 x minus 2 would converge if that was less than 1. And setting that up as a summation, we could have 4/3 times the summation from 0 to infinity of negative 2/3 x minus 2 to the n power. So we're using this formula, x to the n power. Our a is 1. Our ratio, or x value, is negative 2/3 x minus 2. So we're centered at 2. And this summation, if we wrote it out, 4/3, as we sum from 0 to infinity, we're going to take the negative 1 out of here for the numerator, negative 1 to the n, and then 2 to the n, and then x minus 2 to the n. That's our numerator. In the denominator, we have 3 to the n. So the summation, n equals 0 to infinity. Now we're going to put the 4 inside here and the 3 inside here. So if we have 4 and 3, then this term would go away, multiplying it through, putting it into our expression. Our numerator becomes negative 1 to the n, and we have what, 2 to the n plus 2? 2 to the n plus 2 power, and then x minus 2 to the n. And then in the denominator, 3 to the n plus 1 power. So here's my expression as a geometric power series. And then I want to find the interval of convergence. So that would happen when we had this term up here, negative 2/3 x minus 2 less than 1, and negative 1 is less than that term. Multiplying by 3/2, we would have negative 3/2 is less than x minus 2 is less than positive 3/2. So just flip-flopping those around. Then adding 2 to both sides, we would have positive 1/2 and positive 7/2. So our interval of convergence is between 1/2 and 7/2, where that ratio, where our expression, absolute value, is less than 1, if that converges. Example 4, we're going to find a Maclaurin polynomial for f of x as 1 divided by 1 plus x squared. Now we saw one similar to that in the last lesson, but I believe that the square was on the outside of the denominator. So in this case, remember our pattern. 1 over 1 minus x is the expansion of 1 plus x squared plus x cubed, and that's x to the end. And it's geometric if the absolute value of x is less than 1. So we know it's going to converge if the absolute value is less than 1. And here in this case, if we rewrite this to look like this pattern, we have 1 divided by 1 minus negative x squared. So this is our x value, or our k value, if you thought about it as 1 over 1 minus k. And expanding that out as a summation from 0 to infinity, if we use this x here for our particular series, that's negative x squared to the n, then our summation is going to go from 0 to infinity. Pull the negative 1 out, so it's going to be an alternating series, negative 1 to the n, x to the 2n, and that first, to write the first 4 terms using this expansion, we would have 1 minus x squared plus x to the 4th minus x to the 6th, and so on. So these are our first four non-zero terms. Now, part B asks us to find the interval of convergence, and we could use the limit comparison test. Let's see, n approaches infinity, and we have x to the 2n power. So we want to do 2n plus 1 divided by the original x to the 2n, absolute value. So we have x to the 2n plus 2 divided by x to the 2n makes our limit simplify as the absolute value of x squared. So x squared is always positive. We got x squared. So x squared is less than 1. And our interval of convergence would be anywhere between negative 1 and 1, so it would converge here. Part C, we want to use our calculator to compare f of x to the first, I think they said 4, wasn't it? To the first 4 terms of the series from part A. What do you notice on the interval from x equals a half to x equals 2? So if we put in our calculator the summation, and I'll let you do this on your calculator, from n equals 0 to 3, let's see, we know we were centered at 2, right? Is that correct? Oh, from the first 4 terms, okay. So I would want to do negative x squared to the n power. So that summation of those first 4 terms would tell us negative 51. Now, when x is a half, our y value is going to be 8/10 by substituting back into our original function, f of x. And what I'm not going to do on my calculator, because it takes too much time to set it up, I will show you my results. If I graph the function f of x, 1 divided by 1 plus x squared, it's a curve that kind of looks like that. This is my f of x function. And then if we graph our Maclaurin series, which was the first 4 terms, the 1 minus x squared plus x to the 4th minus x to the 6th, that looked like an upside down 6th degree. This is my Maclaurin series. So centered at the origin. So this point, 1/2 and 8/10 matched, but when we got over here to 2, the graph went rapidly down here. So at 2, out here at 2, on my Maclaurin series, my y value is -51. So that Maclaurin polynomial changed rapidly downward from our red original function. And you can explore that on your calculator. Example 5 has given f of x as cosine x squared. Let's use substitution in some known power series. Well, we know our cosine power series. And if I say cosine x squared is my power series, I've got 1 minus my n squared over 2 factorial plus my value to the 4th over 4 factorial minus our value to the 6th power over 6 factorial. And we're just substituting x squared in for where our x is in the cosine pattern. Remember, it was alternating signs and they went on even powers of x. So cosine x squared would expand to be 1 minus x to the 4th divided by 2 factorial plus x to the 8th divided by 4 factorial minus x to the 12th divided by 6 factorial. And as we move up, our summation is going to go -1 to the n, x squared to the 2n, because that's the power for cosine, or the expansion for cosine, divided by the quantity 2n factorial. So we have this one. And part B, I believe we're going to need this expression again, because on part B, they're wanting us to take the derivative of our series. And if this is our f of x, let's see, we're going to write that down. This is our f of x. Then our f prime of x, term by term, this would be 0. The second term would be -4x cubed divided by 2 factorial. And then 8x to the 7th over 4 factorial minus 12x to the 11th over 6 factorial up to our general term. And our general term derivative is going to be 4n times x to the 4n minus 1, because I'm combining these two to make that a 4n, and then divided by the quantity 2n factorial. So like we've seen through the chapter, we can take derivatives term by term up to the general term. Example 6, if we're given arctan of x and it's centered at 0, let's find a power series representation for f of x that's known as Gregory's series. So we already saw from example 4, let's see, what do we know? I think we've got to go back and use example 4. F prime of x is 1 divided by 1 plus x squared. That was our x. That was our example in part 4. And that expansion was 1 minus x squared plus x to the 4th minus x to the 6th, and so on. And we know the derivative of arctan is this same expression. So if we integrate dx over 1 plus x squared, we would be integrating that right side, 1 minus x squared plus x to the 4th minus x to the 6th plus so on and so forth, dx. We also know from example 4 that 1 over 1 plus x squared was the summation from 0 to infinity of negative 1 to the n, x to the 2n. So arctan, switching colors here, arctan of x is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 when we take the antiderivative of this. And centered at 0, our plus c again would be 0. So tan inverse can be expressed as a general summation formula from n equals 0 to infinity of negative 1 to the n, and then if we take the antiderivative of this, it would be x to the 2n plus 1 divided by 2n plus 1. So this is our power series representation for f of x. That's called or known as Gregory's formula. Now, if we check the interval of conversion, we know that this is going to converge if x is less than 1. So if we check x equals negative 1 for an endpoint in that summation, then we have this portion, negative 1 to the 2n plus 1 divided by 2n plus 1, and the limit at infinity is an alternating harmonic series. So we know that this is 0, and that would converge at that endpoint. And x equals 1 is going to also create the same situation as n approaches infinity at 1 to the 2n plus 1 over 2n plus 1. We got 1 in the numerator and a large number in the denominator that's also 0. So that likewise converges, and our interval of convergence would be from negative 1 to 1. Our radius of convergence is 1. And then our final note here on this problem, Gregory's series converges for negative 1 to 1 inclusively. And if we let x be 1, the result is called the Leibniz formula for pi, which is a pretty cool, famous thing. You can look that up on the internet, watch videos on YouTube about it. There's proofs for that. 1 over 2 to the n plus 1, 2n plus 1. They will use proof by induction, I believe, to show you that this sequence, when x is 1, sums to pi over 4. So just a kind of cool little trivia fact there. Then we have one more example. This one's pretty tedious. We want to find a power series representation for x squared divided by the quantity 1 minus 2x squared. The very first thing I'm going to do is pull that x squared off the top, separate our f of x, and then think about this portion here. We want to look at this portion. So we know that 1 over 1 minus 2 to the x can be written to be the summation from 0 to infinity of our 2x to the n power. So 2x to the n power can be written that way. So these two are equal. And if you take the derivative of 1 divided by 1 minus 2x, So the derivative of 1 over 1 minus 2x will give us 2, 1 minus 2x in the denominator, quantity squared. So this is close to what we want, but it's not exactly. So let's take the derivative of both sides. So we can think about the derivative in terms of x of the 1 over 1 minus 2x, and then taking the derivative of our summation for 2 to the n x to the n. We know we've got 2 over 1 minus 2x quantity squared is going to be the summation for 2 to the n times n x to the n minus 1. We got to think about this a second. If you go back to check 2x to the n power series, we get 1 and 2x and then 4x squared. But when you take the derivative of a constant, let's see if I can, the 2x to the n, we get 1 and then 2x and then 4x squared as we let n go from 0, 1, 2, and so on. But I'm taking the derivative right here. So when we take the derivative of this, we get 0. And you want a constant as your first term, so we're going to have to let n be 1 in this case to get a constant as our first term. But if we want to rewrite it so we get n equals 0 down here, then we could show that 2 over 1 minus 2x quantity squared could be written with our n starting at 0 to infinity. If we took 1 away from this, we're going to add 1 here, we're going to add 1 here, and we're going to add 1 here. So we would have 2 to the n plus 1 times the quantity n plus 1 x to the n. And we're still trying to recreate our x squared on the outside times that original function. So let's do a little math trick here. Let's multiply the left side by x squared over 2, and we'll multiply our summation by x squared over 2. And that will help us get rid of the 2 on the numerator, but keep the expression being the same on both sides, and give us our original function here. So we're going to get x squared divided by 1 minus 2x quantity squared. This was what we started with. And we have 2 to the n plus 1 times n plus 1 times x to the n. And we're going to put the x squared inside and the 2 inside. So that's going to give us the summation from 0 to infinity of 2 to the n plus 1 times n plus 1. And if we bring this in here, we have x to the n times x to the second. So that's going to be x to the n plus 2. We're going to put the 2 on the denominator. And then we could reduce this down. So 2 to the n plus 1 divided by 2 would be the summation from 0 to infinity. And this would simplify down to get rid of that. So we'd have 2 to the n plus 1, x to the n plus 2. And they wanted us to write a power series. So we've got our power series. Our f of x can be represented by this power series. And let's say you wanted to write the first 4 terms. If we start at 0, our first term is x squared. And then when n is 1, our second term is 4x cubed. When n is 2, our third term is 12x to the 4th. And when n is 3, our fourth term is 32x to the 5th. And that continues on. So you could write the power series this way, or you could use that power series to write the first 4 terms or expand that Taylor polynomial. Okay, that finishes Unit 10, Lesson 10.